sense? I would say generally no. Because if you're going to see it, I mean, I guess theoretically, but like, there has to be less out than in for endothermic.
Okay.
So generally, I can't think of an example of an endothermic reaction that has flame or like things like that. But you're thinking in the right sense.
So like, couldn't it be like it has flame and then immediately turns like to like nitrogen or something, or like has cold with nitrogen, so it's just freezing cold?
I don't know of anything that does that, but that would be endothermic emission. And
So were there like exciting endothermic reactions, or are they all just boring?
great point. Most of the time, the endothermic ones are not as, at least as we would deem as exciting, because they don't have flame, they don't explode, which is what you normally are like looking for, right?
Is there endothermic reactions that freeze it immediately?
I'll show you next time my favorite endothermic reaction, which to me is like the coolest one, but it's not the same as it is endothermic. So yeah, most of the time. Okay, with this idea of heat change, let's remind ourselves, we talked about this, remember I dropped the leg of our chair? You guys remember that activity? Okay, so this is kind of just reviewing that here a little bit. So when you have a hot object and a cooler object, or less hot object, okay, when you put those two things together, the heat is going to equalize. That's why when you hold onto the leg of your chair, after a while, it stops feeling cold because the heat has equalized.
But that means your hand is colder too, but the chair is warmer than it was.
The difference is our hand doesn't really change a ton because we're like a living thing.
So we just keep putting heat in?
Yeah, like we're using our own heat. But theoretically, yes, your hand in a sense is losing heat.
But it's just
Our body just regenerates it, right? But if you were to put like two things that are not living, right? So if I take like a hot metal, right? So if I heated up these scissors, right? And then I put it next to like a cold metal, right? This in a sense is what happens. The idea is that the molecules transfer that heat as they collide, right? Not in a collision in that they're reacting. I shouldn't leave scissors around in my face. But that they collide and then they can transfer that energy and then it gets equalized out. Okay, so that's what we mean here when it talks about, okay, that the collisions between the particles allow it to transfer. One big thing as you're visualizing and understanding heat, put a maybe extra star next to this, heat always flows from high to low. Because it's always about equalizing the energy out. Annika.
So when like two particles hit each other and like one's way hotter than the other one, is it like evenly transferred out and so they're both like the exact same every time?
Ooh, that's a good question. I would say no, because it would depend a lot on the collision. Like, how did they collide, and like, did they hit perfectly, or was it just like nick the side of it? Like, so there's always some amount of transfer, but I wouldn't always say it's like a perfect. So that's why it like takes a while, is because they just keep moving, but then eventually it is equalized. Does that make sense?
Yeah.
Yeah, good question. So keep in mind that when we talk about it, right, it's that the average kinetic energy, right, becomes the same. Okay? So today's goal is to take this concept of X over endo, and we're now coming to the mathematical side of it. So our objective today is I can calculate heat and enthalpy. Now I want you to notice that these two things are not the same. Heat is not enthalpy. They're connected, but there's two things we're learning how to calculate today. And that will really help you mentally if you make sure you keep them separate. Okay? All right, I think. Oh, sorry, let's get these last blanks in. Sorry, I said this, but we didn't fill it in. So equilibrium is that idea of when you reach that thermal balance between the two, and then their temperatures are the same. That's why, once again, if I were to bring some snow into this room, it would melt, is because the heat's going to flow from warm to cold until it's balanced. Until the puddle of water is the same temperature of this room, right? It's going to transfer that heat over.
Okay, let's say we turned off like all of the heat coming into this room, and then we just put loads of snow in here. Would the room get like colder, but the snow would also melt?
Sounds like a fun experiment.
I think we should do
Like, I mean.
So there's no excess, so we're not adding any heat to it.
And like everything's closed off, and it's just like a massive bucket of massive, and then the room.
Because the room's gonna transfer the heat it has into the snow.
And the snow's gonna melt, but the room will overall be a bit colder.
Yeah, because we've lost heat in the process of it melting.
Gotcha.
This should be our next experiment.
So you're saying that if it's really, really hot in a bucket of snow,
Yeah. Yes, on a really hot summer day, all you have to do is cool out your room and go get a bucket of snow.
On a hot day, yeah.
So, when you have like frost and windshield and hot water on any cracks, why does that happen?
That does a little bit more with the structure of glass. In that when the glass is cold and then you get that, glass is one of those kind of covalent network ones a little bit. And so that quick contrast of like when the bonds are so rigid and it's cold and then all of a sudden they get movement, that's what causes the glass to kind of shatter a bit. So yeah, great connection though.
why with the covalent like things, why is it that like diamonds are super strong but glass is super breakable?
It just depends on how the covalent network is. So carbon is a covalent network of like, so if I'm a carbon in a diamond, I'm bonded to one here, one here, one here, and one here on all four sides. And that's how every single carbon is in a diamond. It's a four-way bond. And so it's just like really, really strong versus like other ones are like maybe just a two-way bond. Or like, it's not like, I don't know, I need to hold the picture that might
Is like graphite like the layer one?
kind of like graphite, how graphite's like flat, really strong, but like vertically not. So, yeah, kind of like that with glass a little
So,
bit.
diamond is the strongest covalent network that we know of, or?
Yeah. Okay, this equation right here is going to be our new best friend today. It's nicknamed the MCAT equation. That's what we're calling it in college. Because it's MC, that's kind of like an AT. And if you're in science, you know what the MCAT is?
Yeah.
Mass, speed of light, change in temperature?
Close. So the MCAT is a test you have to take to get into medical school.
I knew it. I knew it.
Like if you're going to go into med school, you have to take the MCAT.
So I'm gonna take.
No, it's okay. It's just like in college, it's like a big deal. Like if you're going to go into med school, then you're stressed about the MCAT. But anyway, so this is on our formula sheet, so we don't need to memorize it, but we do need to know how to use it and what it tells us. Okay? So let's label our variables. So Q, and it's not my fault. I don't make these equations up. So if you don't like the variable and what it represents, don't blame me. Q is heat.
Okay.
Okay?
I mean,
Make it a French person.
For energy, right?
M is mass.
I was right on that.
what? That's ridiculous. Mass?
Now, Tyler brought up a good one. C is the speed of light in our other equation. In this one, it's the specific heat of the substance.
I feel like C is always the speed of light. Of course, it's not the one time.
I know. Most of the time, they don't reuse variables, but that's one of the times. And then delta T means, change in temperature.
There's like so many shapes.
Caitlin, did I push play?
Yes.
Oh, shoot. Did I set that up or not?
There's a lot of energy, like specific heat, and change in temperature. Like,
Yeah.
it almost sounds like the same thing, basically.
It is. So what we're taking into account here are the different components, okay? So the goal here is with calorimetry. Okay, calorimetry is the fancy word of, hey, I'm going to do an experiment to figure out the heat change. Calorimetry.
Like
Oh.
calories and geometry. Had a baby.
I like calories.
Well, the suffix of metry, like in geometry, is just the study of. So it's the study of calories, just like geometry is the study of geometric shapes.
I thought we were going to use a different type of
The enthalpy one, we'll get to that one.
guys need to open up
Okay,
yourself. I don't get, like,
with calorimetry, everybody,
go like that.
in your focus here.
It was horrible.
So if we were to do the reaction we did at the beginning with our fruit snack, but to do it as a calorimetry experiment, we would need to perform that reaction in a closed system that could trap in the heat so we could measure the actual change in temperature that was happening.
Like a box.
Yeah, kind of. So there's a lot of different types of calorimeters, which is the device you use. The most common kind, which we'll use next Tuesday when we do our lab, is this. Not one cup.
No way.
But like, I use these in college. This is not just like me being cheap for you guys. Like, styrofoam cups do a really good job at trapping in heat. So you can do a reaction inside of it with a thermometer there and figure out how much heat is being released or absorbed through the temperature change. Now with our reaction, obviously some reactions wouldn't work well in this because they would like melt it. So they do have what are called like bomb calorimeters, which are metal containers that you do the reaction inside of that can handle explosions and things like that. But then it can measure how much heat is being released in that explosion process. Okay? Say it again.
That's the answer for the gummy bear.
Oh, we need a bomb calorimeter to do it in, I guess so. Now, the idea of a calorie, this is how they figure out calories, is they literally just burn that piece of food. Like, so if you just take a Cheeto and you burn it, and you measure the amount of heat that's coming off, you can convert that into a calorie. Because that's what our body does, is we just burn the food, and then we get that energy out. So that's how, like, in like nutrition, that's how they figure out how much a calorie of something is by doing a calorimetry experiment.
So is there a place that can burn food for science?
Yeah, sure. I don't know what its official name is.
The FDA just burns
But
food.
like that's like, yeah, the FDA when they're like testing something new and like, well, how many calories is this? That's someone's job. Is it?
So what you're saying is that junk food is a better source of fire because it has more calories than, say, like other things.
Sure seen it.
Well, that's why.
So if you're traveling the woods, burn the bag of Cheetos versus like
Bag of almonds.
yeah,
Yep. Yep.
So you
Yep.
want to
eat
eat
the almonds, burn the Cheetos.
So when you're eating and you're like using your calories and like burning them, are you actually burning them or like?
Not in the same sense of like a flame, but in the same sense of the bonds breaking and new bonds forming. Yeah, that's what like our stomach acid is doing, right? Is it's breaking those bonds and then new bonds get formed.
So is
But no, there's not a. We're not dragons. We're not fires inside of us.
so
Annika, Betty, did have.
Okay, so if you're trying to like burn calories while you're like running or something,
Yeah.
you have to like create heat to burn them off, or is it with like no? Because I've heard it's like you're breathing because the like oxygen goes in and then takes the carbon out, and that's like how you burn calories.
Yeah, because it's the process of breaking the bonds, right? We need to break the bonds that are there and then form bonds that are CO2, and then the CO2 comes out of us.
And that needs like heat from you.
It needs energy, right?
So it's
Which typically is heat, right? Say that again.
like it's our breathing that burns the calories?
Yeah, so when someone loses weight, it's all coming off as CO2.
Okay.
That's the only way it gets out of us.
If you just breathe really fast, like you're
Yep.
exercising like
I mean, not quite, but like,
Okay.
yep. That's the only way we can lose our mass is through the CO2 that comes out of us. It doesn't just like go away from us. Unless you get like lasered off or something. Betty, did you have a question?
No.
Okay.
I was just gonna ask, we were talking about how earlier your body replenishes that heat when you're holding on to something. Does it do that by burning calories?
Yeah. Yep. Yeah, that's why like if you would burn more as a cold actually because
So
your
if you take a
body's
cold
trying to-
shower, you're burning calories.
There's actually people who like, that's one of the because have you ever heard like some people are all about like cold showers?
Yeah.
They, like,
Yeah, but that's what's called sadness.
yeah.
okay, here's what we're gonna do, everybody ready? So we're gonna take this equation. Give me your focus here. Back up front. We're gonna try a problem finding the Q value. Now I want to emphasize here there's two parts. Right now we're finding heat. Heat is Q. Okay, Q is heat. We're then going to take the same exact problem, do part B, and find enthalpy. Okay, but let's start with just using what we have and finding the heat. Okay, so make the problem into a story, right? When you read FRQs and it's an experiment type thing, visualize it, right? See yourself, even if you're like, I don't understand it all the way, create a simple image of what's going on. So in this problem they say, a student mixes 50 milliliters of a 1 molar HCl and 50 milliliters of NaOH in a coffee cup calorimeter. So if I were to do this in front of you right now, what would I do?
Pour some liquid and then pour some other liquid.
Perfect. I'm just taking two liquids, pouring them together in my cup. Okay? All right, in that process, we measure that the temperature changes from 21 to 27.5. The goal is to calculate the heat change for the reaction, assuming that the calorimeter loses a negligible quantity of heat. Underline that sentence right there. Assuming that the calorimeter, just that part, assuming the calorimeter loses only a negligible quantity. What is significant, or why is that sentence there?
It's like saying that you have to assume that the calorimeter is doing its job and the heat isn't just like escaping.
Exactly, because if it wasn't, then the data I'm getting isn't valid. Now, because in this class it's all on paper questions, they're always going to have that sentence. When we do our lab on Tuesday, we won't have that sentence because we'll be able to measure and figure out that error factor of how much heat is actually escaping from our system. But this actually makes our job a lot easier when you just assume that it's doing its job, okay? All right, it tells us the total volume of the solution, it tells us the density, and its specific heat. So my first step when I'm problem solving is, well, what am I trying to find? Q. All right, so let's write the equation for Q. So Q is MC delta T. Okay, so when I'm trying to solve a problem, I start with what am I trying to find, and then just take it piece by piece. So I'm trying to find Q, so M is?
1.0 grams per milliliter.
So that's the density, we need the mass. Ooh, Austin's close, so we know we have 100 mils. Mass needs to be in the unit of grams, which the density is 1. Right, so I'm just writing out just so you can see it, but it's just 100 grams. That's why they gave us the density, was so that we could get from volume to mass. Keep in mind, M should always be the total mass of the cup. Okay, not just like one part of it, but everything there, the total mass is M. Because mass is very dependent upon the size of your fiber, right? If you have more gummy bears, more heat, right? Less gummy bears, less heat. So the M
gummy bear?
is very important. Okay, all right, C, what is C? Good, and it's always going to be given. C is the specific heat, and it is constant for a substance. This is the specific heat of water, which is honestly what most our problems are going to be using, because they're molarities, and molarities are in water. So it's normally going to be this, but if it wasn't this, they would give it to you as it is.
What is G times K?
So it's what specific heat tells us is it tells us if I had 1 gram of water. Okay, so imagine 1 gram of water is like maybe like a half a teaspoon. Okay, so if I have half a teaspoon of water, the specific heat tells us that it would take 4.18 joules of heat to raise that by 1 degree. So if I want to heat up my 1 teaspoon from 20 to 21, I have to put in
Celsius, right?
that much heat in Celsius. Yes. So the specific heat takes into the factors of how things heat up differently, right? Some things heat up very easily, and some things take a lot more to heat up. So that's what the specific heat value is taking into account. For example, most metals, very, very low specific heats, because metals heat up very rapidly, right?
How do they study this? Just by trial and error, like?
Yeah, they just test it for that substance, and it's just that constant value.
Like, we'll just put energy into this until it goes up a degree.
That's my guess, is they literally just get 1 gram of it, and they just very controlledly put energy in until it went up, and then they have their value. So, questions on what specific heat is? Okay, and then delta T, what is that?
Changing temperature.
Good. It's always final minus initial. Okay, so final minus initial.
27.5 minus 21.
6.5.
Yes. 6.5? Alright, questions on any of my numbers or units that I plugged in before we do the math? Debbie?
Is Celsius directly proportional to Kelvin then?
Oh, great question. By change, yes.
Okay,
So they're not the same, but they're on the same scale.
okay.
So a change in Celsius is the same as a change in Kelvin.
Okay.
So you don't have to like do any conversions. Good observation.
I don't think I did that.
Any other questions so far?
So like, if you changed a Celsius degree, it would change 1 Kelvin?
Yes. But like 20 degrees Celsius is like 293 Kelvin. But to go down 5 degrees is the same on both scales.
That makes sense.
All right, I think I got, if I remember from last period, like 2017.
Yep.
Oh,
All right.
I thought
Hey, that could be a
sounded
year
wrong.
in 700 years.
So wait, would that be in Celsius, 2,717 degrees Celsius, or?
So check our units here. So there's a gram unit here.
We're not allowed, I would.
That's gonna cancel with that gram unit.
So for measuring.
And then the K's are so joules.
Which Q should always be in the unit of energy, which is a joule. Technically, it could be in a calorie if you wanted to convert it. But in this case, it's always going to be in a joule. All right, questions so far with using MCAT?
But that's my information energy.
Okay. One side note, and then we'll talk about the enthalpy side of it. Okay. Oh, before I say anything, don't say it out loud. Or a smiley face in your head. Figure out, is this reaction, we did the math, but is it exo or endothermic? Don't say it out loud. Based on what we did and what the problem tells us, is this exothermic or endothermic? Okay, on the count of 3, show me your vote. Ready? 1, 2, 3. We're about 50-50, I think. If you are saying exothermic, have a smiley face, you're correct. So, let's talk about why, because once again, if you said endo, I wouldn't say you're confused, I think it's just you're looking at it the wrong way, maybe, right? So someone who said exo, help us out, how did you identify as exo, Robbie?
Well, in the problem, it said when you mix the two solutions together, the temperature increased from 21.
Going to the data, if temperature goes up,
It's XO.
is exothermic, right? Because that means the heat is being released as the process occurs, right? Anyone willing to share that said endo of why they said it, or I would read your mind of why I think you did? Seth?
I said it because I thought we're measuring the solution, and if it increased from 21 to 27, it was warmer.
Oh, because you're saying the solution absorbed the heat, and so it would be endothermic? Is that what you're saying? Yeah, and that's where like it can be, endo and exo are simple, but it can be easy to just like be focused on the wrong side of it, right? Of once again, we're always observing the outside, right? The thermometer, which went up, isn't the system. It is a surrounding. So if the thermometer went up, that heat had to come from the system. So thanks for sharing, Seth. Now, another thing we talked about last time were signs. Did anybody look at this and say, oh, it's positive, so that's endothermic? Maybe not. That last period, that was a common reason. Anyone know why that's not true here? Because it is positive, but it's not endo. Michael, what do you think?
Because that's the heat produced, not.
Very good. It's the delta H. This is not delta H. Delta H is negative for exothermic reactions. But Q is just how much heat was released, right? Okay, any other questions so far? All right, with this idea of it, it's important to recognize once again, as we mentioned from the beginning, the first law of thermodynamics, that heat can't be created or destroyed. It just gets transferred. And so this kind of goes along with how Seth was looking at the problem of that whatever amount of heat the reaction releases, the calorimeter is absorbing, or vice versa, right? If this is absorbing heat, then it's taking it from, and so they will always be the same. Heat isn't created or destroyed in the reaction. So that blank right there should say conserved. Q is always equal.
RxN is reaction.
Say that again.
RxN is reaction.
Yeah, RxN is an abbreviation for reaction. Now, just because Q's are equal, does that mean the change in temperatures have to be equal between the two different things? No, right? You can have a lot of different things multiply to equal 10. Right? So keep in mind, if I mix hot water and cold water together, they're going to equalize to a stable place, but their change in temperatures probably won't be the same. But the amount of heat transferred between the hot water and the cold water will be the same. So the heat transfer is always the same, even though the individual temperature amount, right, might not be the same. Now, with this idea of transfer, we do need to be cautious not to mix it up with what's known as thermal conductivity. So we talked about specific heat. This is what we'll be using. Here's some other examples of some common specific heats. Right, so like iron has a specific heat of 0.45, copper 0.38. They very quickly heat up. It doesn't take a lot of energy to heat up a metal. But the thermal conductivity is the ability of that metal to then transfer that heat back out. Izzy?
What has the lowest specific heat that we found?
I don't know. I'll be back to you. The lowest one on this is lead, but I don't know outside of that if there's other metals that are lower. But what I want you to notice is, did I put lead on that one? Oh, I should have. But what this tells us is how quickly that heat then gets transferred. Meaning, when you touch it, if it is hot, do you feel the heat? Right? I don't know if you've ever experienced, but aluminum doesn't transfer heat very quickly. Right? You can have aluminum in the oven, like aluminum foil over food, and you can like take it off with your hand and it's not too bad. But if I were to touch the pan itself, I'm a goner, right? But that's all about how quickly that heat is being transferred.
So if we're looking at that, that means fiberglass transfers it really quickly?
So let's fiberglass.
At the bottom.
Yep.
And human tissue's up there too, so if you touch fiberglass that's really hot, you'll definitely feel it really quickly.
Yeah, because it would also transfer through like your body. So just kind of recognize that specific heat is not the transfer. It's about the ability to hold a particular amount of heat, right? So like water does a really good job at holding its heat in, which is why it would take forever for like a lake to completely freeze through, right? Is because it holds onto its heat really well, which is good for our environment, right? Otherwise we'd have frozen solid lakes. Okay, all right, let's try the problem. Oh, we're skipping this. It's already in order in your notes. I just forgot to change it on here. Okay, come flip the page over and you should find this next. We're skipping 6.5 and doing 6.6, but I found it was better to do it back to back. Okay, so H is enthalpy, so put enthalpy on that blank line.
What's enthalpy?
Enthalpy is H. Enthalpy is the amount of heat released or absorbed by a chemical reaction at constant pressure in relation to the moles. Okay, so we have Q and we have H. Q is heat, H is enthalpy. moles. Q is just the heat. So here's kind of an example to hopefully help you see the difference, okay? So in our gummy bear experiment, or fruit snack experiment, right? Okay, if we were to measure the amount of heat today, would it be the same if I were to do the reaction again but put 2 fruit snacks in?
No,
Why not?
because there's more sugar to burn.
More mass, right? MCAT, Q is gonna get bigger. Delta H would never change. Delta H has the same value for a given reaction every single time. Any thoughts of why?
Because it's not like adding more is gonna change the rate, like, or,
Because it's in relation to the moles.
Is that what you're gonna say, Seth?
Yeah, just like per mole it's the same.
Because as Q gets bigger, the moles are getting bigger. So if H is a ratio of them, it's always gonna be maintained. So for example, the burning of wood will always have the same delta H value. But the Q value is very dependent upon how much wood you're burning that day. So in the end, delta H is way more helpful to us because it truly compares how much heat something is releasing. You could be very deceived by saying, oh, this has a huge Q value. But maybe you had to use 10,000 grams to get that Q value. So this will come into play in our lab on Tuesday as you guys will be designing or selecting the best reaction for a hand warmer. In that the Q values aren't really what you want to focus on. It will be the delta H values because the Q value, once again, is dependent upon how much you put in, which is going to play a role in the hand warmer you make, right? You don't have to put in 1,000 grams into a hand warmer to make it work well, right? Okay, so now this reaction, I'm sorry, it's not my fault. It's not on your formula sheet. I don't know why. It drives me crazy why there's like 4 of them throughout the year, they just don't give me. But this is one of them. So make a note to yourself somewhere that I need to just know this. It is simple, but I still hate that they don't give it to you.
Why did they decide that some of them they can put on and some of them they don't?
That is my argument
We're
exactly.
gonna make it so you fail the test. And this is your
Like, and
So-
are the rules just like putting it on my thing and just be like a little underline? Can I write on my formula paper?
Oh yeah, you can. So like
Honestly,
if you
like,
like as soon as you get in there, I guess
like
if you want to
study,
like
memorize, and then jot them down as fast as you can.
yeah, you totally
Oh, yeah.
could.
right before you get the
That's
test,
what
you're
I
like
would do.
reading
That's
off.
what I do for all my
Just
math
like write
tests.
them on there. So it's Q of the reaction
You write them on-
over the moles of the reaction. Okay, now notice there is a slight change in Q in that we do need it in kilojoules when normally it's found in just joules. So we'll have to do that slight conversion and then we'll just divide it. So let's try, notice it's the same problem we just did. But now the question says, what is the enthalpy change? I'll be honest, most of the time on the AP test, these are a part A and part B they love to do. Where part A is find Q, part B is find enthalpy.
And they give you the Q equation but not the H equation?
Yes.
Why?
Why is H enthalpy and not?
We just need to have a discussion.
Why? Like they
Q is
I need to
because.
set up a meeting with the official.
Be like,
excuse
can
me,
we
have some
email
issues
someone?
here.
Can we email someone and be like, hey, this doesn't make sense at all. Would you please give some reason why to? Or put them all on the paper? I don't understand. If all of us email it, then it might work.
Okay, so we need Q and moles.
I would go with.
Okay? Now, we already found Q from part A. That was our 2,717 joules. Now, we do need to change it into kilojoules, which is the same as like a kilogram to a gram, so it's 1,000. So we're going to move the decimal 1, 2, 3. So Q is 2.717 kilojoules.
Oh wait, why did we change it?
Delta H is always in kilojoules.
Gotcha.
Okay, now the bottom part is we need the moles from the reaction.
So is that just converting the grams into moles?
So if we had grams, we could go grams to moles. In this case, we don't have grams. We have volume and molarity. Now the difference here is with MCAT, the M was the total mass. In delta H, the mole is only the limiting reactant. because once you run out of the limiting, the reaction will stop. And you're not gonna get any more heat once it stops. Okay? So look at the problem with me here. So we're mixing HCl and NaOH. So our answer is we need which one is limiting. To find the limiting, you figure out how many moles of each you have, and then compare it to the balanced equation, see what's gonna run out first. Now in this case, we have equal amounts of both, right? We have 50 mils, 1 molar, and the balanced equation is 1 to 1. So in this case, they're both limiting, and so you just use one. It doesn't really matter. We'll do an example next time that has it where they're not the same, and you'll be able to kind of test out that way. But for now, I'm just going to convert. So I have 50 mils of my acid, and I want to convert this into just the mole. Okay, so I'm going to get out of milliliters into a liter. And that way I can use molarity. So capital M is moles over liters. Once again, I know this does nothing mathematically, but it's important, I think, to see it. So I divide that through, and I get 0.05 moles. Questions on the mole part of it for now? Yeah, thanks.
How do you know it's one polarity?
It was given.
Oh.
Yeah,
Oh.
and molarity, if you're in volume, they're gonna give you a molarity, so. All right, I plugged that in, it was like 54?
54.34.
So
34?
Yeah.
enthalpy equals 54.34?
Yep, so my enthalpy or my delta H is 54.34 units.
Kilojoule?
Kilojoules per mole.
Yeah, both stay because they don't cancel, so it's kilojoules per mole. Now the final piece is the sign of it. The sign of your delta H needs to match what type of reaction happened. So was this exothermic or endothermic?
Exo?
And so the sign needs to be negative. So you need to make sure the sign
This is
matches the reaction. And what happens is it's always going to be opposite. You're always going to have to flip the sign of delta H versus what it shows you, due to the fact of the system versus the surroundings idea. But I just like to focus on, does my answer make sense based on the problem? Annika?
So do you have to have the heat to calculate the enthalpy?
Yes. Yeah, you can't find enthalpy without Q. Well, back up. Using calorimetry, you have to have Q. After our lab next time, the rest of this unit is we're going to be calculating enthalpy in different ways. Kind of similar to like our rate law, like how we found like all the different ways to find a rate law. We're going to talk about there's different ways to find delta H.
Okay, that makes
But if you're doing an experiment, you have to have Q.
So there's like different equations that relate to delta H?
Yep. So, any other questions? Okay, so your homework tonight, 6.4 is practicing MCAT and delta H. And then you have 3 short AP classroom quizzes, kind of practicing what we talked about last time with exo and endo, the graphs, those type of things. So, okay?
Should I hold on to this still?
Yeah, keep your yellow paper, we're still gonna use it. I forgot. Okay. Any final questions before we pass back your test?
Oh, sure, I'm trying to see how bad I feel.
Okay. Bacon.
Feel really bad?